Hello all, welcome back to my YouTube channel all about VLSI. In our previous session, we have seen how to design a synchronous counter and what are the steps which we required for designing a synchronous counter. This and all we have seen in our previous session. Now in this particular session, let us try to design a 3-bit synchronous counter without actually referring to that particular steps. That means how we can design it. First of all, let's see the count sequence. So the first initial state is 000 for a 3-bit synchronous counter up counter. Next is 001, 010, 011, 100, 101, 110, and 111. And this is Q2, Q1, and Q0. So this is my count sequence. This is my count sequence that is from 000 to 111, which I have. How can I design my counter just by seeing this table? If you carefully see this Q0 sequence, it is getting continuously toggled. Initially it is 0 and next it is 1, next it is 0, next it is 1, next it is 0, next it is 1, next it is 0, next it is 1. So I can simply write this T flip-flop. I can simply draw this T flip-flop and I can provide the clock and the input will be simply 1 and this is my Q0. So initially Q0 value will be equal to 0 and after that Q0 value will be equal to 1, next 0, 1, 0, 1, 0, 1. Okay, I can just simply give my T flip-flop input as 1 so that I can design this T flip-flop. Now, if I want to get my Q1, I can see the pattern in Q1. If my Q0 is equal to 0, my present value of Q1 is equal to 0, next value of Q1 is also equal to 0. But if my Q1 is equal to 1, present Q1 value will be equal to 0 and next Q1 value is equal to 1. It is getting toggled. Here we can see present Q0 value is equal to 1, then present Q1 value is equal to 1 and next Q1 value is equal to 1. It is getting toggled if your Q0 is equal to 1 at present. And if your Q0 is equal to 0, then the next Q1 value is 1 only. That is, it is not no change. And if your present Q0 value is equal to 1, then there is a toggle in the next state of your Q1. That is, it is getting toggled from 1 to 0. So that means I can just simply connect this Q0 to another T flip-flop. I will draw the other T flip-flop diagram. So this is my T flip-flop and this is my output Q1. And I will connect the clock with this. And I can connect this Q0 simply to this Q. And I can connect this Q0 simply to the input of my T flip-flop. Then what is happening if this Q0 is equal to 0, then the next state of your Q1 is not getting changed, it is constant. And if your Q0 is equal to 1, present Q0 value is equal to 1, then only your next Q1 value is getting toggled. Okay, so that means here if you have 0, Q0 as 0, then Q1 is getting constant, the next state is constant. But if your Q0 is equal to 1, then your next value of your Q1 is getting toggled. That is how we are connecting by seeing this pattern. And if we want to get the Q2 value, okay, first let me draw the third flip-flop. This is my T and this is my Q2. And I will connect the same clock to the third flip-flop also. Now, coming to my Q2 value, it is equal to 0, 0, 0, 0. If you carefully observe, my Q1, Q0 values are equal to 0, 0. Then my Q2 is 0 and the next state is also equal to 0. And if my Q1, Q0 values are 0, 1, then my present state is 0 and next state is also equal to 0. And if my Q0, Q1 values are 1, 0, my present is equal to 0 and next is also equal to 0. But if my present values of Q1, Q0 are 1, 1, then my next value of Q0, Q2 is getting toggled to 0 to 1. Here we can see if both the values of my Q1 and Q0 are equal to 1 only, then my Q2 is getting toggled from 0 to 1. And again, if my Q1, Q0 values are equal to 0, 0, then my Q2 value is getting then my Q2 value is constant. Here we can see my Q2 value is constant. And whenever my Q1 and Q0 values are equal to 1, 1, then my Q2 value is getting toggled to 0. Okay. And if we have Q0 value here as 1, then Q1 is also getting toggled to 0 and the next value of Q0 is obviously 0. So this is how we are going to find out the pattern from this sequence. Then we can simply draw Q0 and Q1, connected to an AND gate, and we can give the output to the input of this flip-flop. So this is how we can draw our 3-bit synchronous up counter. And if I want to draw 4-bit synchronous up counter, then what I can do, I will just write down the syntax. So I want to draw a synchronous 4-bit up counter. I want to draw a synchronous 4-bit up counter. Then how to draw this 4-bit synchronous up counter? Same process. So I will draw the 4 bits 0, 0, 0, 0. This is my Q3, Q2, Q1 and Q0. So it is nothing but 0, 1, 1, 0, 1, 1. This is 0, 0, 0 and 1, 0, 0, 0, 1, 1, 0 and 1, 1. This is 1, 1, 1 and this is 0, 0, 0, 0, 0, 0, 0. Okay, and followed by next sequence, let me draw it Q3, Q2, Q1 and Q0, and this is 1 followed by 000. 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. And this is my sequence which I am going to draw for my 4-bit up counter. Now, this is my 4-bit up counter and how to draw the design. So first of all, let us draw the 4 T flip-flops. This is one T flip-flop, second, third and fourth. This is my T3, T2, T1 and T0. Q0, Q1, Q2 and Q3. So we can see from here, let's say this is T0, Q0, T1, Q1, T2, Q2 and T3 and Q3. Okay. And these are all connected with the same clock. These are all connected with the same clock. And we can see the value of Q0 is getting toggled every time. That means the value of T0 is equal to 1. Okay. Here we will get the value of Q0. And we already know the relation between Q0 and Q1, that is whenever your present value of Q0 is equal to 0, then your next value of Q1 is equal to 0, and whenever your Q0 value is equal to 1, then the next value of Q0 is getting Q1 is getting toggled. This we already know. Okay, and if your present value of Q0 is equal to 0, then the next value is same only. That means I'm just simply going to connect my Q0 to T1. Okay. Now coming to Q2, this relation also we know. If your Q1, Q0 are equal to 1, 1, then only there will be a toggling condition in the value of Q2. Or else, if your Q1, Q0 is equal to 0, 0, or either one of them are equal to 0, then your next value of Q2 is not getting changed. It is constant only. But if your Q1, Q0 values are equal to 1, 1, here we can see the value of Q2 is getting toggled. Okay. That means we have already seen this. Q1 is connected and Q0 is connected to a AND gate and the output is given to the input of the T2. This we have already seen. Now coming to the T3, we can see coming to this T3, if Q2, Q1, Q0 are equal to zeros or either one of them are equal to zeros, then everything this Q3 is constant only. Okay, but if Q2, Q1, Q0 are equal to 1, then Q3 value is getting toggled. We can see here it is equal to 0 and here it is equal to 1. And again, if your Q2, Q1, Q0 is equal to 0 or either one of them are equal to 0, then Q3 there is no change. Okay, that means what I am going to do is this output and this output I am going to give it to one more AND gate and I am going to give it to the value input of the fourth flip-flop, that is input to T3, and here I am going to get my Q3. So this is how I am going to design my 4-bit synchronous up counter. 4-bit synchronous up counter. And if I want to design my n-bit synchronous up counter, and if I want to design my n-bit synchronous up counter, then how to design this n-bit synchronous up counter? The design process is simple. Let's see. So this is my LSB flip-flop. This is my T. This is my 1. Input is 1. This is T0 and this is Q0. And followed by this is second flip-flop. This is T1 and Q1 and T2 and Q2. So on Tn and Qn. and every flip-flop is getting the same clock. Every flip-flop is getting the same clock. So on to my clock. Okay. Now, here we have already know Q0 is connected to T1 and T2 is connected by the output of your AND gate, and this Q2 so on, and this output so on, it is connected to one AND gate, okay, to Tn. So this is how we are going to design a n-bit synchronous counters. Now let's try to design our BCD up counter. Let us try to design a synchronous BCD up counter. We have seen how to design a asynchronous BCD counter. Let us try to see how to design a synchronous BCD up counter. For a synchronous BCD counter, first of all, let us try to draw the state diagram. So the state diagram will look like this. The initial state is 0, next state is 1, followed by 2 and 3, 4, 5, 6, 7, 8, and 9, and followed by next it is equal to 0. So this is my BCD synchronous BCD up counter. Okay, and coming to the state. So from this state diagram, I will draw the table, excitation table. Let me draw the excitation table for this particular state diagram. So this is my Q2, Q3, Q2, Q1, Q0, and this is my Q3 plus, Q2 plus, Q1 plus, and Q0 plus. Let me write it down. This is my Q3, Q2, Q1, and Q0. Q3 plus, Q2 plus, Q1 plus, and Q0 plus. And I'm going to use a T flip-flop again. T3, T2, T1, T0. If you want, you can use any flip-flop. I'm using T flip-flop. So what is my first initial state? It is equal to 0, 0, 0. Next is 0, 0, 0, 1. Next is 0, 0, 1, 0. Followed by 0, 0, 1, 1. 0, 1, 0, 0. 0, 1, 0, 1. 0, 1, 1, 0. 0, 1, 1, 1. Okay, and Q3, Q2, and so if my present state is equal to 0, I can see from the state diagram that is my next state is equal to 1. So it is 0, 0, 0, 1, and this is 0, 0, 1, 0, and this is 0, 0, 1, 1, and this is my 0, 1, double 0. This is 0, 1, 0, 1, and 0, 1, 1, 0, 0, 1, 1, 1. Just I'm seeing the state diagram and I'm drawing it, and followed by 1 triple 0. This T3, T2, T1, and T0. So I have 0 triple 1 and 1 triple 0. So this is 1 triple 0, 1 0 0 1, 1 0, 1 0, 1 0 1 1, 1 1 0 0, 1 1 0 1, 1 1 1 0, 1 1 1 1. Okay, and this is my 8 9, and after 9 we will go to 0. Okay, by seeing the state diagram I can see from after 9 I am going to go to 0. Then after 10 I will consider it as a don't care, and this is also don't care, and this is my don't care, and this is my don't care, and this is my don't care, and this is also my don't care. So I have filled this particular table, the values of T3, T2, T1, T0. I have filled it by following the excitation table of T flip-flop. Now I need to fill this. So my T0 it is equal to 1, and here T1 it is also equal to 0, and T2 is also equal to 0, and T3 is also equal to 0. And coming to this, it is equal to 1 only, T0 is equal to 1 only, and coming to T1 it is 0, and T2 is also equal to 0, and T3 it is equal to 1. Okay, and remaining all are my don't cares, and remaining all are my don't cares. This is my don't care, and this is my don't care. Now, by seeing this excitation table, let me draw the. So let us try to form the circuit. First of all, let us draw the equation. Let us write down the equations for T0, T1, T2, and T3. From the table, I can see the value of T0 is equal to 1. Okay, the value of T0 it is equal to 1 itself. And coming to value of T1, let us draw the K map for this. This is my Q3, Q2, Q1 and Q0. Q1 bar, Q0 bar, Q1 bar, Q0, Q1, Q0, and Q1, Q0 bar. Q3 bar, Q2 bar, Q3 bar, Q2, Q3, Q2, and Q3, Q2 bar. This is 0, 1, 3, 2, 4, 5, 7, 6, 8, 9, 11, 10, 12, 13, 15, and 14. So my minterms are here. These are 1, 3, 5, 7, and the remaining all are my don't cares. 1, 3, 5, 7, and remaining 8, 9. Sorry, my don't cares are from 10. So 10 is my don't care. 10, 11, 12, 13, 14, and 15. These are my don't cares. 10, 11, 12, 13, 14, 15 are my don't care. So if I group them, so this is one quad which I can form, and this is one quad which I can able to form. So my T1, which is nothing but I can take Q3 bar common here and followed by Q0, Q3 bar Q0 plus Q1 Q0 is my T1. T1 is nothing but Q3 bar Q0 plus Q1 Q0 is my T1. Coming to T2, the minterms for my T2 are 0, 1, 2, 3, 7. That's it. 3 and 7. 3 and 7. And don't cares are 10, 11, 10, 11, 12, 13, 14, and 15 are my don't cares. So I can make a group of this quad. That's it. Okay. So my T2 is nothing but Q1, Q0. My T2 is nothing but Q1 and Q0. My T1 is nothing but Q3 bar Q0 plus Q1 Q0. And from the table, let me write down the minterms for my T3. T3 is nothing but only T3 is nothing but 7 and 9. 7 and 9. And remaining 10, 11, 12, 13, 14, 15 are my don't cares. 10, 11, 12, 13, 14, 15 are my don't cares. So I can form a quad here and I can form a dual here. So it is nothing but Q3, Q0 plus Q1, Q0, Q2. Okay. And let me check the others also. This is my equations which I am getting. And here there is no need to form this quad because it will become a redundant. T1 is just simply Q3 bar Q0. And this is my Q1 Q0, and this is T3 is nothing but Q3 Q0 plus Q1 Q0 Q2. Now using these equations, let us draw the circuit. So this is my T0 and Q0 and Q0 bar, and we have connected our clock here. So we are connected T0 as 1 from the equation we can see. And coming to T1, this is my T1 Q1 and clock is connected to here. It's a synchronous circuit and T1 is nothing but Q3 bar Q0. Okay, let me draw the other flip-flops also. This is T2 and Q2 and this is T3, Q3 and Q3 bar. And this is my clock. Now I'm going to connect this Q3 bar and Q0. Q3 bar and Q0 are connected. So I'll write down Q3 bar here. I've connected to a AND gate and I've given the connection to the T1. This is my Q3 bar. Okay. Now coming to T2. Coming to T2, it is nothing but Q1, Q0. Coming to T2, it is Q1 into Q0. Let me draw the Q0 here, and which is given to T. And coming to T3, it is nothing but Q3, Q0, Q3, Q0, and Q1, Q0, Q2, Q2, Q1, and Q0, which is given to a OR gate, and this output is given to T3. So this is my BCD synchronous up counter. Let us try to verify it. If my initial value Q3, Q2, Q1, Q0 it is equal to 0, 0, 0, 0, then obviously next value of here Q0 is equal to 1 and Q1. So from the equation we can get the Q1. Q1 is nothing but it is output of the first T1. So T1 is nothing but Q0 into Q3 bar. So I will write down here T1 is equal to Q3 bar into Q0. What is Q3 bar? It is equal to 1, and what is Q0? Q0 is equal to 0. Output will be equal to 0. So T1 is equal to 0. So Q1 is also equal to 0. No problem. And coming to T2, let us write down equation for T2 also. Q1 into Q0. Q1 into Q0. So Q0 is equal to 0. Q1 is also equal to 0. Sorry, Q0 is equal to 1 and Q1 is equal to 0. So T2 is equal to 0. Q2 is also equal to 0. And let us write the equation for T3 also. Q2, Q1, Q0 plus Q3, Q0. So Q0 value is 1, but these two values are equal to 0. And this value is also equal to 0. So T3 is equal to 0. Q3 is also equal to 0. So like this, let us go up to 8. Okay, let's say we have reached up to 8. Now what will be the next value? Q0 will be equal to 1 because T0 is always 1. Coming to Q1, Q1 is nothing but T1. We should check for T1. T1, we can see Q3 bar. Q3 bar is 1 and Q0 it is equal to 1. So T1 is equal to 1. So Q1 will be equal to 1. So Q3 bar. So Q3 bar means Q3 is equal to 1. So it will be equal to 0. So obviously T1 is equal to 0. Q1 is also equal to 0. And coming to Q2. Q2 means we should check for T2. T2, it is nothing but Q1 into Q0. Q1 is equal to 0. Q0 is equal to Q0 is equal to 0. Okay. So 0 means T2 is equal to 0. Q2 is also equal to 0. And coming, so here we can see the value of your Q2 is equal to 0. So obviously this whole value will be equal to 0. And here the value of Q3 is equal to 1, but the value of Q0 it is equal to 0. So this whole value will be equal to 0. So the T3 value will be 0. So there is no toggle. Q3 will be equal to 1 itself. This is nothing but our BCD. And if the present value is equal to 100, let's say, then what is the value of your Q0? It is equal to 0 itself. And what is the value of your Q1? For getting the value of Q1, we will have the value of T1. T1 is nothing but Q3 bar into Q0. Q3 bar is nothing but 0 and Q0 is nothing but 1. So obviously this value will become T1 value become 0 and Q1 is 0 itself. And coming to Q2, what is the value of Q2? We should check for T2. If T2 is equal to 1, then there will be a toggle condition in Q2, or else if Q2 will remain the same. So coming to the value of T2, that is nothing but Q1 into Q0. Q1 is equal to 0 and Q0 is equal to 0. So the T2 is equal to 0. There is no change in the value of your Q2. And coming to Q3, for getting the value of Q3, we need to have the value of T3. So T3, Q2 is equal to 0. That means this whole value will be equal to 0. And Q3 is equal to 1. And Q0 is equal to 1. So T3 is equal to 1. So if the value of T3 is equal to 1, then there is a toggle in the value of Q3. That means it will become 0. So we can see after reaching the value 9, it is getting to 0. So our diagram is, so our particular circuit is working correctly. So this is how we are going to design our BCD synchronous up counter. So that's all about this particular video. If you like this video, please like, share, and subscribe to my YouTube channel, all about VLSI. Thank you for watching this video.